Okay, so we are the Distributed Spectrum Sensing and Channel Assignment Group. This is the team.
Um,
Oh, sorry.
that's fine. This is me, and it's
This is me. I'm Sam.
This is me. I'm Aditya. Yeah, go ahead.
So the problem we're trying to figure out in our project is we're trying to figure out some kind of solution to spectrum underutilization, which is caused by static assignments of channels before your device is just given a channel to use, and that causes, when people aren't using their channel, a lot of underutilization. As seen in the graph, there's holes between what's being used, which could be used more efficiently. Next slide, please. So one solution for this is using cognitive radio. What this does is dynamically assign channels as devices want to use them, instead of having one assigned beforehand. This allows more devices to be used when devices aren't, because they'll use the same channels, which is much more efficient than what's being used now. And two methods of doing this that we look at are energy detection and artificial intelligence. Energy detection is just reading what's going on right now, seeing what channels are available to be used, and just picking one as you see it. And then the artificial intelligence way is using data outside of just, is there an open slot, and running it through some kind of algorithm to figure out what might be the best channel to use at this time. Next slide, please. So there's 3 steps to cognitive radio. The first step is spectrum sensing, which is just observing the spectrum, seeing what channels are being used, seeing how strong different signals are, etc. The spectrum analysis is the smart part of it. It's the cognitive part. This is where you actually figure out where you're going to use what channel you're going to use. You'll use the data from the spectrum sensing and then run it through some numerical formula or artificial intelligence formula to figure out what you're going to do. And then finally, you have channel assignment, which is you use the result from that analysis and you act on it and you use that channel.
Okay, so some of the terms that we're going to use in the rest of the slides are SDR, that stands for software defined radio. And that's essentially just a normal radio, except the processing of the signal, which is usually done through hardware components, like mixers and filters, are instead done through software. And USRP stands for Universal Software Radio Peripherals. And these are the specific family of SDRs that we have on the orbit nodes, which we use for testing. UHD stands for USRP hardware drivers. And these are just the drivers we use to communicate with the USRPs on each node. And finally, we have GNU radio, which is another piece of software that we use to configure the USRPs on each node for transmission frequency, sampling rate, gain, etc. Or if we need to perform any transformations on the transmitting end or the receiving end of the signal, we can do that through GNU radio as well. So like I said, we used nodes with USRPs on the orbit network, and those nodes were used to model cognitive radio nodes. And below is a USRP X310, which we use in our experiments mainly. So the first thing that we did is we started to use the USRPs to send and receive signals with the customized transmission parameters that I talked about earlier, again, like frequency, sampling rate, gain, etc., across the orbit network, and listen in on other nodes. And this is an example of what we see on the receiving end of one node.
in order to improve our efficiency of the spectrum sensing, we are going to have some data for the machine learning. So we create data collection in the grid on the orbit lab. So we can see in the right, we use 2 nodes for transmit, 2 nodes for receive, and 1 node for observe. And the left side is the USRP devices for transmission. And we write several Python files and then try to run them and collect the data and load the data to the MATLAB for the further steps. Next slide, please. We have another approach, which is the GNU radio using USRP. As we mentioned before, the GNU radio is another piece of software used to configure the USRP on each node for frequency, sampling rate, and any other transformation. So the graph is just a simple GNU radio. You can see I have 2 blocks. One is the signal source, and the other one is the USRP sink. We're trying to use this schematic to transmit a cosine wave, which has sample rate at 10 megahertz and frequency at 1 megahertz with amplitude 0.5. Next slide, please. As the same as the GNU radio, we also simulate the steps on MATLAB. You can see the graph here. It's also a cosine wave, and we can see there are 2 peaks at positive 150 hertz and negative 150 hertz, which is caused by the cosine wave. Next slide, please. This is the comparison of the simulation and the real USRP devices. The left one is the simulation, and the right one is the real USRP devices using the grid on the orbit lab. We can see that both graphs have the 2 peaks at positive and negative side. In a real USRP, there's a peak at 0 hertz, which is due to a DC offset of the received signal, which is displayed on the right. Next slide, please.
So for the next steps for future projects, with enough collected data and correct metadata assigned to that, we could train an artificial intelligence to recognize which channels are occupied and which channels are free to use. But it would require a lot more data than what we were able to collect. And also, as I said, it would require the correct metadata for like the frequency of transmission, the location of the nodes, etc. So we could also use more complex GNU radio operations to perform the necessary calculations for the energy detection approach. This includes like the fast Fourier transform and that kind of thing. And we would also have to detect things like the noise floor and stuff like that. So that is another possible approach for the future. And finally, we could also implement or find an implementation of the IEEE standard for cognitive radio, though implementing the standard ourselves would be difficult to complete in like 2 or 3 weeks, which would be the rough time frame we want to complete something like that in. So finding an implementation would be more desirable. So yeah, thank you.